All right, so one of the first things that I want to do is I want to talk about the history of the atom, where we've kind of gone from, thousands of years ago, what we understood to where we're at today as far as what we understand about the atom. Because again, what we want to look at here is we want to know uh, how everything works, all the materials around us, what their properties are. We want to know how they're bonded together. We want to know information about it, and the more that we know about the atom, the better. And instead of me just saying, this is where we're at today, I think that it's kind of interesting to see the process. You guys take science classes. It's interesting to see the evolution of that throughout time, and maybe we can be a part of the next steps. To do that, it's sometimes nice to see where we've come from and where we're at today. So first I want to start off with Egypt, 2000 BC, so a long time ago. Even then, though, they knew about 10 elements. Most of them were metals. Metals are pretty easy to work with. They could melt them down and they could form things out of them. But they did know about carbon and sulfur as well. A little bit after that, so 400 BC, somewhere around there, in Greece, Democritus, he had an idea, and what he said was, he said everything is either a void or it is being. And by void, he meant that it's a vacuum, it's nothingness, it's the emptiness, it's the absence of stuff. And being is the physical stuff that we interact with. He actually coined the term atom. He called it the being and infinity of atoms. He says that it was indivisible and eternal. He proposed that there's some discrete form of matter that you can't break up. And to be honest, I find this amazing. Over 2,000 years ago, somebody came up with the idea that if we break something enough, we can't break it anymore. And it's not the fact of it gets too small to break it. We don't have the machinery to do it. He just says it just can't be done scientifically. Everything's made up of something, and at a point it can't be broken up more. And to me, that's just amazing, because everything that we see on a daily basis breaks down, right? I can take a rock, I can break it in half, I can break it in half again, I can break it in half, break it in half, and I can keep doing that. And so to kind of go and say, I propose that there is this really small scale where we can't do that anymore, I just find amazing. So this is a little bit of a side note, but also in Greece at the time, there were some other people proposing theories. And one of those theories was about the 4 essences or elements. There's actually 5 of them, the 5 essences and elements. Those are fire, earth, air, and water. The 5th one would be ether or spirit. And there were ideas that you could combine these, same as you can combine atoms together. You combine fire and air together and you get hot. You combine earth and water together, you get cold. And so, the different ideas about how the world works. And that was just a little bit of a side note. But over the centuries, more and more elements were discovered, and people started making lists and tables of these elements. And in the late 1700s, and from what I remember, it was like the late 1700s, like 1798, 1799, a French scientist made a list of simple substances. Now, I don't speak French. This is a picture of what was published. I can, just because it's similar to English in some ways, I would assume here at the top that it means the simple substances, the substances that are simple, something along those lines, and then the table of the simple substances. And if I kind of scroll through here again, even though I don't speak French or read French, I see some things that look familiar. Things that look kind of like oxygen, or hydrogen, or sulfur, phosphorus, carbon, cobalt, mercury, nickel, zinc. So some things that are like, okay, it makes sense. This could be a table of elements. But if you scroll back up to the top and think about it, again, I don't speak French or anything, but I see this thing that looks like lumiere. And lumiere means, from what I understand and from watching Beauty and the Beast as a kid, means light. And so something about light, there's a problem there. And underneath that, you have this thing that looks like calorie. And again, that's a problem, because the idea is that light and energy are not substances, and so they're not elements, and they shouldn't belong on a table with substances and elements. So close, but not quite a true table of elements. Early 1800s, Dalton made what we call the first table of elements, the one that we recognize as the first table of elements, not the periodic table, but just a table. And he gave 5 principles. First one, he said all matter is composed of atoms that are indivisible and indestructible. He got that from Democritus, the idea of the atom. He also said that all atoms of a specific element are identical, or in other words, when I take an oxygen atom, this oxygen atom looks identical to every other oxygen atom in the universe. Same thing with carbon and hydrogen and helium and all those other atoms. They are identical. And again, this is something that I think we take for granted, but it's amazing that people came up with these ideas. Everything that people saw, everything that we see, they have slight differences, right? It's the idea that every snowflake is a little bit different. Every rock that you see, every grain of rice that you see, they are all slightly different. He came up and said, well, you break something down small enough and they're not anymore. They are 100% identical. He says that atoms of different elements have different weights and chemical properties. So the idea that they look identical, they weigh the same thing, they're going to have very specific chemical properties that we could use. Atoms of different elements can combine in simple whole number ratios to form compounds. That's your basic chemistry there. That's your stoichiometry and your reactions that you deal with in chemistry. And the idea that atoms can't be created or destroyed, that when a compound decomposes, the atom looks the same as it did before you started. So that atom recovers completely unchanged. And so here's again a picture of his elements, and I'm sure there's a key somewhere of which one of these are. This is more of a picture table here, where we have 1, which is a circle, and 2, which is a circle with a dot in the middle. And by looking down a little bit further, he shows some of these compounds that we can mix things together with. And this one here says oxygen with hydrogen. And so here my guess would be that this number 2 at the top, this circle with the dot in it, would be the oxygen. And the circle without the dot, just the plain circle, would be the hydrogen. So some interesting stuff. And so we give him the first credit for actually having a complete table of the modern day elements that we know. It doesn't necessarily have all the elements, but the ones that they knew up to that point was a pretty complete list. So we fast forward a little bit more, and in the 1860s, Dmitri Mendeleev made what we call the first periodic table of elements. And it was very interesting. The idea was he started looking at these atomic weights, and he started listing them in a row so that they were in some type of order. And he noticed that at a certain point, the atoms started having similar chemical properties. Remember up here, what Dalton said was that atoms of these elements have different weights and chemical properties. So he ordered them in weights and then kind of listed out their chemical properties, but he noticed that at a certain point it kind of went back to this chemical properties started repeating. Even though the weights kept going up, the properties kept repeating a little bit. And so kind of put all those in a list of the ones with similar properties. And so we now have this periodic table. Things tend to repeat in some manner. And it's very interesting because what he decided to do was where we didn't have anything that fit a specific spot, he left it blank. And he said there's something that should be here, but we don't know what it is yet. And we can see that here. There are some question marks, like next to 68 and 70. There are some question marks of what should be there. We weren't sure. Next to 45, question marks. The other thing that happened was he found some errors and made some fixes. Found that, well, this material, even though it has a little bit higher or lower atomic weight, doesn't really fit periodically where we have it. And so he would take them and he would switch them and no longer have them in atomic weight order and say it fits my periodic system better. even though they're no longer in order by weight. Some people didn't like that, so they kind of said, you can't do that. And as he went back and people looked at it, they went and found that they had calculated the weights wrong, and found out that his periodic system still worked. And because of he switched it, they found that there were errors, and a lot of errors were fixed. All right, so we get our modern day table of elements eventually, starting with that one. If I need to look something up quickly online, I go to ptable.com. I am not advertising for them or anything. I'm just telling you one that I like to use. It's organized well. It's easy to find. It's easy to remember and to type in to find it. And so we have this periodic table. We have all these groups, and again, we can see all these periods. We have group 1 here, all these in a row. We have group 2, all the way over here to our noble gases in group 18. Off to the side, we have some information about things like its weights, its energy levels, melting points, boiling points, electron affinity, things like electronegativity, different things that are going to be useful to us possibly in the future. One thing that I did want to point out is, again, as a kind of when I was in high school, middle school, I'd see these periodic tables up in my teacher's room, and I saw these down here at the bottom, these ones that didn't necessarily seem to go anywhere. They kind of seemed like they were out of place, and it kind of had this little arrow or this little block saying they go here. But I think one thing I like about p-table is you can click this button called wide, and what it does is it shows you where they actually fit inside of the periodic table. And it shows you that we kind of have this system where we have this stair step that keeps walking its way down. Something interesting, not necessarily super important at this moment, but it's interesting to note that. I get why they do move it out of the way, because this doesn't fit well on a piece of paper or on a poster. And since we don't use those atoms as much, we can just kind of say, hey, they're there, but we're going to put them at the bottom, almost as a footnote is the way I looked at it when I was a kid. But they are there, and they are important. All right, so we get up to the point where we kind of say, all right, we start having this table of elements. I want to talk now about what we're understanding about the actual atom itself. Late 1800s, early 1900s, J.J. Thomson proposes what we call the plum pudding model of the atom. And the idea here is that we have this positive sphere, and so the whole sphere is positive. And so what I did was I made it red, and I kind of put this plus going through the whole thing to show the whole thing is positive. And that these electrons are distributed uniformly throughout this positive sphere. And the idea of plum pudding, from what I understand, pudding is or was used as a term kind of just for dessert. A lot of times it was more of a cake. And so if you were to cut up plums or raisins or nuts or something inside of a cake or a muffin, you would want those things evenly distributed throughout them. You could cut that muffin in half, open it up, and that the bread, the cake part, that would be kind of like this positive sphere. It's just uniformly everywhere. And then you'd have these speckles of whatever you decided to put inside your cake or muffin, and those would be your electrons. Said there were no protons, everything was just positive around it, and that the electrons could move. They could move right through the middle. There was no nucleus or anything. They could move wherever. Obviously, because they were negatives, they probably didn't want to interact with each other, but they could move anywhere inside this positive sphere. Okay, so he has this idea. Great. But we have to test it. We can't just say, you know what, J.J. Thomson has this great idea, let's run with it. No, let's test it. And so a few years later, Rutherford and Marsden do an experiment. And what they do is they take gold, a gold foil, and they shoot alpha particles at it. What alpha particles are is they are helium atoms with no electrons, and so they're positively charged atoms. The idea is if the Thomson model is correct, because the whole thing is positively charged, and we have these negative charges uniformly throughout it, the whole thing is kind of neutral. And if that's true, then these positive particles shouldn't really interact with it because it won't interact with something that's neutral. What we should see is we should see all these alpha particles just shooting right through, and on the detector, everything should be right here behind it. What we see instead is, yes, a lot of them made it all the way through. Some of them were scattered a little bit. Some of them were scattered quite a bit, and some of them bounced all the way back a little bit. So you have to take a step back and say, okay, well, Thomson's model didn't do well, the atoms didn't act the way that we assumed Thomson's model would in our experiment. So what would our model look like with the data that we have? So you analyze the data, and what they came up with is we still have some positive and negative, but let's concentrate all the positive to one little spot in the middle, and that's why there is a little bit that bounced backwards, but not too much, just a little bit because it's a small part. There's some that scattered slightly, and those are the ones that got near but didn't quite hit the positive. Because remember, we're shooting positive charges at it, so they're going to interact. They don't interact so much with the negatives because the negatives, they like the positive. They kind of pull it towards it, and they kind of shoot through once they leave because they still have some momentum. Little side note here, because we look here, the majority of the alpha particles made it through, and there were a couple that bounced back and a couple here and there that got scattered. I was a student. I teach students, and a lot of times when things don't work the way that we want, all we say is hey, there was an error, user error, it wasn't perfect. It's very important to notice that Rutherford and Marsden didn't say that here. They didn't say, well, a good majority, I don't know what percentage is, but let's say, 90, 95% of them made it directly through, and there are a few that didn't, but we're going to ignore those as outliers. They got data, and they ran with it. They didn't hide it. They didn't try to change it. They didn't try to say user error. They went with what they found. So something that they did was they found out that because of the data and the number of things that scattered versus the number of things that didn't, that the radius of the nucleus, the positive center, compared to the radius of the entire atom, was on the ratio of about 1 to 10,000. All right, so that's interesting. We have this model. We tested it. It didn't pass, but because of it, we came up with a new model. Great. Does that mean that that's true? Not necessarily. We have more questions now. What about nuclear collapse? How does this nucleus stay together, right? It's just a bunch of positive stuff. Why doesn't it break apart? What's powering the electron if we do have this positive center? We have all these negatives out here. How come these electrons don't come in on itself? What keeps those electrons out? Again, there are things maybe we take for granted. We say, well, obviously because, but it wasn't obvious to them. So 1913, we have a guy named Niels Bohr, and he just graduated from college. He's waiting for a job. He decides that he's going to take some time while he's waiting, and he's going to go work in both their labs, both Thomson's lab and Rutherford's lab. After spending some time there, almost a year in total, he decided that he liked Rutherford's atom, but we needed a model to explain what was going to happen, something better than just the basic idea of what they had, and they needed a model that would predict things as well. So a model to explain, a model to predict. So he built a model, and he tested it. He tried it out. He wanted to see what would happen. And so the idea here again is if we have some type of theory, what do? We test it. And how do we know if our model works? We test it. And if it does work, that means that we're right up to a certain point. No test is perfect. And so it passes our test. That's great. If it doesn't pass our test, that's okay too. We can modify it. We can change it. And that's what we did from Thomson to Rutherford. We changed the model a little bit. But just because it passes a test doesn't mean it's perfect. We can sit back. We don't have to worry about it again. We can find more difficult tests, test a little bit different things, test things a little bit more in depth. Then we can modify slightly after that. One thing that he came up with here was, after testing it out and looking at things, he came up with circular orbits. He wanted to test it, and to do this, he needed to compare his model with some data. But luckily, there was already some data that he could do that with. So now we're going to kind of go back again and look at where this data came from. 1850s, we have Angstrom. And what Angstrom did was he measured emission lines from hydrogen gas discharge tubes. And going back again to my middle school and high school science classes and posters up on the board or up on the wall, I saw posters all the time that looked something like this. And to be honest, I thought it was the most mundane, stupid, boring thing ever, and I didn't understand it. I saw this big black bar at the bottom that just had these colored lines spread out periodically, and I saw this thing above it which was much more colorful, looked like a little rainbow, and at those same spots where those bars were missing, they replaced it with a black bar, a little black line. And I thought to myself, all right, so you just said, here, we're gonna take this little red part here and we're gonna stick it down here. We're gonna take this blue part, this purple part, and we're gonna move things around. I didn't understand it, I didn't get it, it was very boring, but that's what Angstrom did. When you see those things, that's what Angstrom measured. J.J. Balmer, 1880s. He studied Angstrom's number. All Angstrom did was he ran an experiment, got some values, and said, isn't this interesting? And it just kind of sat there. Angstrom looked at the numbers and he found a pattern. And he came up with what we know as the Balmer series. And this Balmer series looks like this equation here. Now this isn't a V, this is a Greek letter nu, and there's a bar over the top of it. Nu with a bar over the top of it is what we use in science as a wave number. And all a wave number is it is the inverse of our wavelength. And it just helps us with some calculations. N is our integers starting with 2. So 2, 3, 4, 5, and so forth. And R is a constant, which is our ionization energy for hydrogen. So what a gas discharge tube is exactly is it is a glass tube that we would fill with some gas, in this case hydrogen. There'd be a cathode on one end of the tube and an anode on the other, and we would allow electrons to build up on the cathode and jump to the anode. Now, occasionally in my notes, you'll see that I write this E with a little minus above it. I use that to mean electron. It's common in for shorthand in a lot of notes that you'll see. Even though I typed this out, I figured I'd put it up there. It's in my notes that I might be posting on Canvas and all that, and that you might see from other classes. Anyways, as this electron builds up and tries to jump across this this hydrogen gas to the anode, some of these electrons are going to crash into the hydrogen gas, and when it does that, it's going to excite the electrons that are in that hydrogen molecule. All right, so we have this picture here. Let me really quickly get my drawing stuff out. And I apologize in advance, I'm not great at drawing on my screen. All right, so what we have here is we have a picture. We have this electron, we call it the incident ballistic electron. It's the electron that starts flying through our tube, and it's going to have some amount of energy. And that energy we can see down here. Let me is a kinetic energy, a 1/2 mv squared. That's the same thing as Q times V, charge times voltage. So that's the energy of an individual electron. What I have here is this is going to be our energy space. That's our energy. And again, sorry for my my handwriting and everything here. Let's say that we have these energy levels here, n equals 1, n equals 2, n equals 3, and so forth. And we have these energy levels, and I have an electron that is sitting right here. If this electron that's flying through the air hits this hydrogen atom that has its electron sitting at n equals 2, and there's not very much energy, there's not enough energy to knock this electron up an energy level, then this electron's just going to fly through, and it's not going to interact, it's not going to lose any energy, it's just going to fly through. But if there is enough energy, if there's enough energy in this incident ballistic electron, during the collision, what's going to happen is this electron can be promoted up to a new energy level, right? Gets some energy, gets bumped up there, that's great. The electron then leaves, and you can see that the scattered ballistic electron, after the collision, the electron leaves, but I have a much smaller arrow here. It's lost some energy. How much energy did it lose? Exactly the same amount of energy as it took to promote this electron. This electron then moves on and does whatever it has to do at that point. Well, it can't stay promoted forever. This electron that hit n equals 2 can't stay promoted forever. And so what's going to happen is eventually it's going to have to fall back down. So it's going to fall down, and as it falls back down, what happens is a photon is given off. So this is our photon. And the energy of our photon is h nu. So I'm going to just put E here for energy of our photon equals h nu. Now remember, this is a very specific distance here for our atoms. The distance from here to here. It's a very, very specific energy difference between there. We call that the energy of our transition. And we actually consider it to be from the top to the bottom. So the energy of our transition starts at the higher energy state and says, where do we end up? It's the falling electron is the energy of transition. All right, we'll go back to this picture in a second, so it'll maybe make a little bit more sense here in a moment. A few quick things. If the incident energy is smaller than the gap between the energy states, then nothing happens. The electron just passes directly through. And that's what I said initially. If there's not enough energy, if this incident energy isn't as big as the transition energy, then the electron goes through, no interaction, no slowing down, no energy change whatsoever. So if there is enough energy from the incident ballistic electron, if there's more energy in that than the transition energy, then during the collision, some amount of energy, and that some amount of energy is whatever it takes to promote that electron, is going to be taken. And it's going to be used up to promote that electron, and whatever is left over, the electron will continue moving. So it'll be moving at a slower rate. It's lost kinetic energy because that kinetic energy has been turned into energy to promote the electron. Now what's going to happen is that electron can't stay up here forever, and it's eventually going to fall. And that's where we get our photon of a very specific wavelength, because that very specific wavelength is a very specific energy level. And so that's what we have here. We have this equation basically saying that the transition energy and the scattered electron energy added together is the initial energy of that electron that comes flying in, that incident ballistic electron. All right, so what is our change in transitional energy? Well, these are both moving electrons. Let's go to our ballistic electron real quick. They're both moving electrons, and so we have a kinetic energy for those two, and I'm just using, again, this equation that's right above it. And so this term here for our change in energy, that would be what we have here. Now, I'm not going to go over this term by term and really get into every little thing. I think this would be good maybe to look at, to think about, maybe to write it out and kind of figure out some of this stuff yourself as well. We can talk about it in classes. But this has the same form as something that we talked about just a minute ago. And it has the same form as the Balmer series. So if we scroll up really quick to the Balmer series, we have that R times something over the square root of 2 squared minus 1 over n squared. That's very similar to this. If I'd make some substitutions, this negative kz squared, what if that was R? And what if this n final was a 2? This would be 1 over 2 squared minus 1 over some n squared. Very, very similar to this Balmer series. All right, so that's something to think about, something to look at. I'll have a picture here to maybe visualize it here in just a second. But the last thing, and I want to touch on this again, I've already talked about it slightly, that this is discrete and quantized. And what that really means is that we can only have an electron per motion if our energy coming in, that incident ballistic electron, is greater than the transitional energy. And if it's not, then that electron's going to fly through and it's not going to do anything. It's going to just pass through, no energy loss, not slowing down, nothing. All right, so I have a quick example here, something to look at. Let's say that I have an emitted photon. So that change in energy goes from 2 to 1. N2, n equals 2, to n equals 1. So that means we go from 2 to 1. I plug in this information and I look at, again, this looks very similar to the Balmer series. I can substitute some things in. And so here I say if we substitute and rearrange, then I get something that looks like this. For the Balmer series, our final n was 2. And I said that our ni's, or our second n, could be 3, 4, or 5. And our KHC, K over HC, is this ionization energy of hydrogen. So very similar. We could pop things in and we could get Balmer series out of this. And so here's our picture. And I'll have you guys can look at this. I have a larger picture of it that I will let you guys look at the end of this video. But there are actually multiple series. The Balmer series is just one of them. And it's the one here that starts at n equals 2, and we promote an electron up to n equals 3, n equals 4, n equals 5, n equals 6. The question is, why was that the first series to be found? Why didn't we find the Lyman series first? Why didn't we find the one that started at n equals 1 first? Or the Passion series, the one that started at n equals 3. How come we didn't see those ones first? And so that's something to think about. It's an interesting thing to think about. So now we're going to go back. So all this stuff is really interesting. We found all this data. We did some math. So now Bohr comes up with some postulates, some things that he has proposed. He proposes that the Rutherford atom is correct. Remember, the Rutherford atom is the one that has a positive nucleus with electrons that are away from the nucleus. He says that classical electromagnetic theory is not applicable to an orbiting electron, which, to be honest, is amazing. It almost sounds like a joke. We have this electron, and we say, hey, we're not going to use electromagnetic theory on it. Instead, we're going to use Newtonian mechanic theory. We say that that does apply to the orbiting electron. And what is Newtonian mechanic theory? That is what we use for planets revolving around the sun. And so the idea is, he says we're not going to talk about this electron using electromagnetic theory. Instead, we're going to use basically gravitational theory, something similar to that at least. I talked about how the energy of the electron is equal to the kinetic and the potential summed together. The electron energy is quantized through angular momentum. And the Planck-Einstein relation applies to the electron transition. And again, that's talking about the transition energy. So a lot of stuff is he came up with. There were some other people doing work at the same time, a little bit before and a little bit after. Not going to get into all of these ones very deeply, but again, it's important to know that they happened and that they were important. Frank and Hertz, 1913, used mercury gas instead of hydrogen gas, which gave us more than one electron, seeing what happens if we have more than one electron. Michelson Morley, they looked at doublets of spectrum lines. Zeeman looked at a spectrum if this experiment was done in a magnetic field. Stark did the same experiment in an electric field. Sommerfeld, he modified the Bohr model by allowing slightly elliptical electron orbits. Instead of perfectly circular orbits, he said, what if they were a little bit elliptical? De Broglie, he said that we could model the electron as a wave. Heisenberg gave us the uncertainty principle, and Schrödinger gave us the wave equation. And so you sum all that stuff together, and what you end up getting is you get our modern idea of what an electron looks like, kind of with the positive nucleus with an electron cloud filling different orbitals. All right, so I wanted to just show you really quickly some slides that I put together with some key things on it. First thing, here is our hydrogen spectrum again. This is what Angstrom and Balmer were doing. And this is that larger picture that I was telling you about. Again, thinking about why was the Balmer series the one that we found the easy one to look at. And then we have this. I found this online. It is a timeline talking about the different ways that we have visualized the atom, starting with Democritus, different very small atoms. We had Dalton, Thomson, where we started looking at positive and negative charges, but the whole thing was positive with moving electrons throughout it. Rutherford, we have this positive center with electrons out here somewhere. And Bohr finally saying that those orbit, the electrons orbit our positive nucleus. And we have this idea now of we kind of have this electron cloud around in our atom. We have this positive center with an electron cloud. So real quick, since we're talking about quantum mechanics, I thought I'd show you really quickly kind of Schrödinger's equation. It's a partial differential equation. Here we have, it looks pretty simple, right? It doesn't look, I shouldn't say it looks simple. It doesn't look big. It looks pretty simple. But really all these variables stand for something a little bit larger. So this H with a little hat on it is called the Hamiltonian operator. It's our kinetic and potential energy. The potential energy might be something simple like our electrostatic potential. And then we have our wave equation psi here, and this is our independent non-relativistic equation for it. Starts getting a little bit daunting if you look down here. You got all this stuff up here, and then we have L, capital L, and capital Y, and you say, okay, well, that's not too bad. I have this L variable and this Y variable. Those aren't necessarily variables that are single things. What they are is they're additional functions in series, and depending on what the values are of our N and our L and our M, they can get very, very complicated and very, very long themselves. All right, so what we do is we take all that information and we have that our wave equation psi is dependent on N, L, and M, and those are our quantum numbers, N, L, ML, and MS. Sometimes this ML is just shown as M, and MS is S for spin. And we have all these possible values for it. Our N can be any positive integer, 1, 2, 3, 4, 5, and so forth. Our L is any n minus 1. So we take whatever n's we have, and we can do from 0 up through n minus 1. Our m is going to be our integers from negative L up through positive L, and our spin is just plus or minus a half. It's the fact that we can have 2 electrons in any given orbital, one with spin up and one with spin down. And what does that mean? All right, well, we have our n number here, and what our n does is it tells us something about our electron's distance from the nucleus, which really is telling us something about the size. We have our L. This is telling us something about our angles. So it gives us the shape of our orbitals. We have our M, which is magnetic, and that's our orientation. And lastly, again, S is our spin. And then lastly, we have this picture, which maybe you've seen in your chemistry class, or again, maybe on a poster somewhere in a science classroom. We have this one here that looks pretty simple. It just looks like a sphere. And then we have these ones that have a couple lobes, some more lobes with a little ring somewhere. This one has 2 rings. This one starts looking like some type of 3-dimensional blossoming flower, starts getting complex. What exactly are all of these things? All of these things are solutions to this equation. If we solve this equation for our different radiuses and angles, so this is in our 3 space, in what we end up getting is we end up getting these shapes, these plots. And what they end up being is they tell us something about the orbitals of our different atoms. And depending on what orbitals the different atoms have, they're going to bond differently. And so that becomes very important when we talk about bonding up a whole bunch of atoms to make solid things such as the table, a computer, a car, or a book, or whatever we're doing. All these things really boil down to really understanding what's going on inside of our atom and what the energy levels are going. Remember, it all goes back to the energy.